So, you all know it. Who of you knows disaster recovery? Oh, I wasn't expecting that. I was expecting a lot more. So, when things go wrong, there is the option of, well, having your work prepared, and therefore you have a disaster recovery plan. There are recovery time objectives, there are recovery point objectives, but basically you should have a backup idea when things go wrong. It's called disaster recovery. But disaster recovery in your data center is like a little bit of ordinary. We have today, let's say, a disaster recovery 1 year later, and in this case, when disaster, how many? 10 years later, and in this case, when disaster recovery hits rocket science, piston maker. Thank you.
All right, thanks for coming. So I'm going to try and tell you a little story about trying to save a dead satellite from becoming space junk with a few little firmware hacking tricks. So very briefly, who am I? I'm a computer science student from TU Berlin, and I play CDF sometimes, where I mostly do like reversing challenges, and I also make some mods for video games. But the important thing is I am not an aerospace engineer. So a logical follow-up question might be, where do I get a satellite from? Well, it turns out my university actually has quite a few of these things. They've launched 30. And the interesting thing is the way these things are funded turns out to be they get funded to be built and then launched, and then they get operated for like a year. But the thing is, a lot of them actually outlast that 1 year lifetime. And so what do you do with them after that 1 year lifetime? And so the uni came up with something called, they did a class basically, which teaches students how to operate spacecraft, and once you pass the class, you can then use the old spacecraft, which don't have funding anymore, to keep doing more science. And so I took this class in 2022 and worked on a satellite called BEESAT-1, but actually today we're going to talk about a much older satellite than that called BEESAT-1. This is a 1U CubeSat, so it's 10 by 10 by 10 centimeters and weighing 1 kilogram. And it's sort of like a standardized form factor, basically. And at the time, this was a pretty new form factor. This was like the 33rd one of those that's in space. It actually was the first CubeSat of the university, too, with like a new team, everything designed from scratch on a pretty low budget. So apparently a pretty adventurous project, I'm told. I was in primary school. And nowadays, there's like 4,000 of these things in space. So it's had like a 1 year primary mission, and it successfully completed that. And the thing that makes it interesting is it's actually in such a high orbit that it's going to take more than 20 years for it to come back to Earth. So we have 20 years to use this thing. One problem, in 2011, so after the primary mission, it started returning invalid data, so like nothing useful. And so they did some diagnosis on this, and they determined, okay, maybe this is like a radiation-related failure. Because in space, there's more radiation, so sometimes parts fail. So what they did is they switched computers. So they had 2 computers on board for redundancy, for precisely this reason, and they switched to the other one, and it worked again. Perfect. Then it happened again in 2013, and they were out of computers. Unfortunate. So at some point, I knew about this and randomly met the project lead at a party at the university, and we discussed this a bit. And did some theories on the precise symptoms, and we eventually actually kind of agreed that it didn't really seem like a hardware failure, it seemed more like a software failure. And so maybe we actually have a chance to bring this thing back to life. So, here's the plan. We're going to figure out how a satellite works, very briefly, then we're going to figure out what the problem is, then we're going to fix the problem, and then we have a new satellite. So, this is a satellite. We don't have time to go through all this in detail. The thing I want to point out is you have lots of duplicated components, and these are organized in these different subsystems, these different boxes. And the subsystems on this satellite are connected together by 2 CAN buses for redundancy. And CAN is a sort of automotive bus protocol, and it sort of found its way into low-cost application where you need reliability and stuff. But we're mostly going to be talking about these 2, the communication system and the onboard computer, because that's the thing that does telemetry. So the communication system consists of 2 identical strings, basically, for redundancy. And each string consists of an antenna, pretty self-explanatory, I think. A transceiver, that's basically like a radio. It can transmit and receive. And then you have a thing called a terminal node controller. And this is like the microcontroller that connects to the CAN bus and bridges the connection to the radio. And this encodes and modulates the telemetry. That's the stuff you send down from the spacecraft to the ground. And receives and then decodes telecommands, which that's the commands you send up to the spacecraft. And what this gets you is half-duplex communication. And so half-duplex in this case means you can only do one at a time. You can't both send a command up and get telemetry down at the same time. So you have to sort of multiplex between these 2, and we'll talk about how that's done in a second. The next thing is the onboard computer, and this is really the star of the show. So this does everything, right? It figures out, it does all the algorithm, right? It collects the sensors, it does telemetry, it processes command, and controls everything. And this is based on an ARM7 TDMI core running at about 60 megahertz. In terms of compute power, I think that's about equivalent to somewhere between a Game Boy Advance and a Nintendo DS. So it's not a huge amount, but you don't need that much, right? You have 2 megabytes of SRAM, so again, not a huge amount. And then you have 2 flash chips. You have 16 megabytes for software, so that's firmware and configuration. And then you have a telemetry flash chip, and that's used to store telemetry data. So this looks like this. These components, all these different components get integrated onto these like 10 by 10 centimeter PCBs. And you can actually see the symmetry between both sides. Right? So this is the onboard computer, and you have one on the left and then one on the right, and they look identical. And they then get stacked up. And once this loads, there you go, they get stacked up like this to make a cube. And then you put a bunch of solar panels on it. And you have yourself a new satellite. You then put that on a rocket and put it in space. So where is it in space? It's located in a 700-kilometer orbit around the Earth. So it's 700 kilometers above the Earth's surface, and it's moving about 7.5 kilometers per second. And so that means it completes one full revolution around the Earth every about 100 minutes or so. And so it's doing this, you can see this as a graphic looking from the North Pole down, and it's doing this mostly north to south. And then the Earth, where Markt Berlin, where the ground station of TU Berlin is, it rotates underneath that, and then you have 2 places in the rotation of the Earth where the ground station and the satellite plane in which its orbit is aligned, right? One's in the morning and one's coming up just now in the night. And when you have that alignment and the satellite passes overhead, then you have line of sight to your spacecraft. And that's when you can actually talk to the spacecraft. So there's a pass just now. And these are typically 10 to 15 minutes long. And you get 3 to 4 of these in the morning and 3 to 4 of these in the evening, right? And that's the only time you can talk to your spacecraft, at least in this kind of orbit. So what do you do in these passes? You try and command your spacecraft, right? So by default, the satellite is not just transmitting telemetry, it's just listening. And that's mainly for power reasons. And so what it's doing is it's waiting for commands. And once it's received a command, it switches into active mode. And what it does then is it's going to transmit these bursts of telemetry data every about 3 seconds or so. And the reason it's doing this in this burst pattern is it needs to leave gaps for you to be able to send more commands up to it, right? And so in those gaps between those bursts of telemetry data, you can send more commands. And then if it goes 60 seconds go by without it receiving any command, then it's going to assume, OK, I'm out of range of the ground station. I'm going to stop transmitting and go back into standby mode. So a question you might ask is, if we only get 15 minutes for 8 times a day, what do we do with the remaining 22 hours and whatever minutes? So there's a concept called offline telemetry. And this is actually kind of common on spacecraft, but it's done differently. Every spacecraft does it a bit differently, I think. And so what you do is, every 90 seconds, the satellite takes its current telemetry data and writes it to flash. And then each of these telemetry transmissions that we talked about, these frames, is composed of 1 set of the telemetry from just now, and then 3 sets of that recorded telemetry from earlier. And so during each pass, you sort of play back what happened during the day to get a complete picture of what's happening to your spacecraft at any one time. All right, that completes the little crash course. Now let's try and figure out what's going on. So this anomaly, we're going to focus on the second anomaly. And this happened in 2013 in March. And so they contacted the spacecraft. And instead of getting data down in these telemetry frames, they were getting quote-unquote empty frames. And we'll look at what empty means in a second. But the other curious thing is, it didn't stop transmitting after that 60-second timeout we just discussed. It just kept going for some reason. OK, so let's cover what empty means exactly. So telemetry is a standardized thing. There's a consortium, a committee for this called the Consultative Committee for Space Data Systems. And they standardize how telemetry can look. And BEESAT sort of follows the standard. Everything green and below in the slide follows the standard. The whole 4 burst thing is kind of a custom thing. But basically, you have these frames, or master frames. And then each master frame contains 4 so-called transfer frames. And this is like the transport layer in a network. And then underneath that, you have source packets. And that's kind of like a UDP packet on the layer below there. And so the first of these transfer frames is dedicated to the live TM from just now. And the last 3, those are dedicated to the recorded telemetry from earlier. Now, I'm not going to bore you with all the details of CCSDS because it's a really long and boring standard, but I'm going to just go through one of the highlights. So this is one transfer frame left on the left. And what you have is you have a magic number in the beginning. That's that ASM, or attached synchronization marker. Then you have a virtual channel identifier, or VCID, and this basically tells you the context of the telemetry, right? Because you can have the same sort of telemetry linked down live, or it could be from a recorded telemetry from hours ago. So that distinguishes between that. You have a master channel frame counter, or MCFC, and this is just a little counter that ticks up every time a frame is sent. And this is useful because you can check that counter, and if there's a gap in that counter, you know you missed a frame. Then you have an APIT, and this really determines the type of telemetry and the format of telemetry sent. So it could be like normal housekeeping telemetry, or a flash dump, or I don't know, other image data, right? And then you have the packet data field, and that's the actual user data, and that's formatted according to that APIT. So this is what a hex dump looks like for a full frame. So you have the different components highlighted again. I just want to illustrate, so this is what it normally looks like, and so this was what it looked like after that anomaly. So you have a whole lot more zeros. But you do still have some stuff left, right? So I'll do you the favor of parsing it for you. So that ASM, that magic number, that's still correct. That little counter thing, that's still correct. But apart from that, the online transfer frames with the live telemetry, those are completely zero. And the offline transfer frame that is supposed to give you historical telemetry, they have a little marker set that says, I tried to get offline telemetry, but there was nothing stored. Interesting. So this is all the symptoms we get. And so now from this, we have to figure out what the problem is. And so to do that, we're going to go through very quickly a flowchart of how the onboard computer generates this telemetry data. So there's two tasks. The first one generates the telemetry, the second one transmits it. So this is the assembly task. This assembles the individual transfer frames, which later then get packaged into master frames. So we have a little timer there at the top called assembly time. And this is that 90-second timer that we talked about that generates a frame every 90 seconds to save it to flash. And it can also go to a lower rate when you actually live downlinking telemetry. And this assembly time thing is a configurable parameter that's stored in flash somewhere. So it's a setting, but it's usually set for 90 seconds. And so when this 90 seconds elapse, it generates a new transfer frame, collects all the telemetry, puts it in flash for later downlinking, and also puts it in SRAM somewhere for live downlinking. Then we have the transmission task, and this is the thing that's actually responsible for sending the telemetry down. So we have first have a 3-second timer on the very left there, and this is to enforce those gaps between frames in which we can send telecommands. So it's waiting until 3 seconds have passed since we sent the last frame. Then it's going to check that 60-second timeout we talked about. And that, again, is a configurable parameter called HDC timeout. But it's set to 60 seconds. And then we're going to construct the master frame out of, we're going to take the online transfer frame from SRAM, from just now, and we're going to read 3 transfer frames from flash to play back the telemetry. And then we're going to attach that magic number and the counter and send it all to the COM. OK. So now what we can do is we can highlight and color all these different things and if they're working or not based on what we've observed. So for example, that 3-second timer, that was normal, even with the empty telemetry. We also know that the ASM and MCFC, those were still written, so those are normal too. But on the other hand, that 60-second timeout, that wasn't working anymore. And we also have no evidence that any telemetry was being written to flash because the marker said there's no flash data. So now the challenge is, what's the commonality between all these things? And if you think about this for a second, you end up realizing every single thing that's broken is controlled by these configuration parameters. So if the HDC timeout parameter was really big, it would look like it's never timing out, but actually it's just timing out after a really long time. And if the assembly time parameter was really big, well, it would look like it's never generating telemetry, but actually just doing that every 50 days or something. So where do these parameters come from? So they're stored in external flash along with the software. So it's a shared flash chip. There's 3 software images in the first part of the flash, and then in the back of the flash, there's one page per subsystem of the onboard computer for parameters. And you have different images because you want to protect against radiation-induced bit flips, so that if one image gets corrupted, you can use a different one. So that's why there's multiple software images. So OK, what could be corrupting these parameters in flash? So I literally just did Control-F for flash.write. And we're going to go through everything that writes to flash, because it's actually not a huge list, because this is supposed to be mostly stable. So first thing, you can do it by command. So there's a command that allows you to change a given setting and adjust it like that. But we didn't send any commands at the time that this anomaly occurred, so we can rule that out. The second thing that writes to flash is something called launch an early orbit phase. And this has to do with all the deploying and stuff that happens just after the satellite leaves the rocket, because it's reconfiguring things there. However, that was done in 2009, so we can rule that out too. And the last thing that actually writes to flash during normal operations is the boot counter of the onboard computer. So every time this thing reboots, it's incrementing a little counter that says, OK, I've rebooted this many times. And that happens on every boot. And that's the only thing that should be really running. So let's have a look at that. So a very interesting thing you notice, first of all, the boot counter is stored in the telemetry system parameter section. They had to put it somewhere, so I guess they decided to put it there. So what happens on every boot is they read the parameter data from Flash, they read that entire page from Flash. They modify it to increment that counter. They then erase the Flash page entirely, and then rewrite it. Now, you might be asking, why do they do that in this convoluted way and don't just directly rewrite it? And that has to do with how Flash works. In Flash memory, or at least this type of Flash memory, you cannot program an individual 0-bit back to a 1. If you want to change an individual 0 back to a 1, what you have to do is you have to erase the entire page to bring it to an all-1 state, like ones is the erased state, and then flip all the bits you want back to zeros. And so they have to do this little dance if they want to do any zeros there. But the problem is, there is a window of time between when that page is erased and when that page is reprogrammed where the entire page is erased. And if at this unlucky moment you have a reset of the spacecraft due to some reason, like power loss or whatever, then you're going to end up with that page entirely erased in all ones. And because these parameters are unsigned integers, all ones is the maximum value, so the spacer is only going to generate telemetry every 50 days. And unfortunately, that's a bit too slow for us to see. So we have a theory of what could be wrong. So now it's time to test the theory. And so we can do that because there's a telecommand that temporarily lets us adjust this assembly time variable. And so we can try and changing it back and see if that helps. We can't change any of the other parameters in that section back, unfortunately. But we can change that one, and that should be good enough to get us some telemetry at least. So this is what the telemetry page looks like when you're operating the spacecraft. And it's this classical cliche thing, right? You have black text, black background, green text. And this is how it would usually look when you're operating the spacecraft, because you just get all these zeros, so there's no valid packets in there. And now we use this little magical little command, and wouldn't you know it, we actually can get some telemetry back for the first time in over 10 years. And so it turns out this thing is fully functional after all, right? All the telemetry says it's exactly the same state it was in 10 years ago in 2013. I also managed to find a telecommand that lets us actually directly dump Flash contents down. It was never used before, don't know why, foreshadowing. But it turns out we can dump this down, and that confirms to us that the section is indeed erased. The thing is, we got some telemetry down now, but we can't operate the spacecraft like this, because a bunch of features are still broken. That parameter page contains a lot more than just that one parameter, and so a bunch of voltages are like wrong because the configuration is wrong, so we need to permanently fix this somehow. But before we do that, let's stop messing around on the real spacecraft and try messing around with one on the ground, because if we mess up something on the real spacecraft, we don't have a replacement in orbit, unfortunately. So we need some development setup. The way this is usually done is you build multiple units of your satellite, and then you have one that you send to space, and that's called the flight model. And then you keep one on the ground to do all your testing with. So you test stuff on the ground before you send it to space, and that's called an engineering model. The problem is, because this thing was broken for 10 years, and they needed the parts for something else, they dismantled that development model, so it no longer existed. So what we did is, because this is a satellite series, I worked on BEESAT-9 in the class, for example, we took one of the later satellite models, and then we swapped components around to make a Frankenstein BEESAT-1, sort of. And that ended up looking like this. So sort of bare bones version of the satellite without the outside skin. You have a little additional board in the middle there with LEDs that tell you like what's on and what's off. And then you have a bunch of stuff hanging off of it. So you have a JTAG adapter off it, and you have that's the transceiver in the top right. I couldn't manage to screw that down, so we just sort of have it laying there. So that gets you JTAG and everything, and so that sorts the hardware side out. And then now the software side. The problem is that no one that worked on the spacecraft still works at the university. But I fortunately did have that contact to that one project lead, and so using that, I could. We managed to piece together the mostly complete set of binaries and source code. The problem is we had binaries, we had source code, but we didn't have symbol maps mapping the binaries to the source code. So unfortunately, I did have to go through and manually disassemble the firmware images and add all the symbols everywhere. It's not super hard, right, because you have the source code, so it's not really reverse engineering, but it's just annoying. So we have that set up. Now let's try and actually fix the issue. So the first thing you might say is, OK, can we just use a command to rewrite that area of flash? Because I mentioned earlier there is a command to do this. And that command is called command write dword. And here's what it does. The problem is this only works in that parameter region. And the first thing it does is it reads a 16-bit size field for that subsystem. Now, unfortunately, that size field is erased. So it's going to read as all ones or 64 kilobytes. The maximum size of a parameter page is 8 kilobytes. This will not go well. The next thing it does is it reads that data into an SRAM buffer, sized for 8 kilobytes. So it will massively write overrun that buffer. But let's assume that works out fine because everything behind there in memory is unimportant. It's not, but let's assume. Then it will erase the flash page to try and do that rewrite in a second. It will modify the buffer in SRAM according to the command. And then it will try to rewrite that 64K buffer into 8K of flash. And this is where they finally have a bounce check, which prevents this from happening. And so what you end up is once a page has been fully erased, you can never again, using the existing onboard software, write to it. It's sort of burned, is the terminology we ended up using. So we need to somehow enhance the existing onboard software. So we need software capability. The problem is, this spacecraft does not support software upload. So we're going to have to get a little bit creative. So the first step so what we're going to do is we're going to basically patch in, we're going to have to do a little weird software upload, and we're going to add in the software upload functionality so we can do a proper software upload later. And the cool thing is, because parameters and software images are stored in the same flash chip, that getting us software upload also lets us directly rewrite that parameter section so we can both fix the bug and just directly fix it. So the first step to doing a software upload, we have to somehow get code into memory. Now the first option might be, can we do it into SRAM somehow? This would be appealing, because SRAM is very safe. It's gone after the next reset. So if you mess something up, it's a non-permanent change. The problem turns out to be we don't have enough time to do that. We get 15 minutes per pass, right? And the spacecraft is unfortunately unstable enough that after one pass, it might just reset and wipe all of that clean. And so we couldn't reasonably assemble like a payload in SRAM. The other thing is there's no actual feature to write to SRAM. So we'd have to do some weird thing where we use parameters of telecommands that we queue up somewhere or abuse some other feature. In short, we could maybe do it, but it's not desirable. And so the only other way to put new code into memory is the the flash. And the only thing that we can use to write into flash is this command write dword command. And that can only write to parameter space. But that turns out to be OK, because this is all one big flash chip, and the permissions are everywhere, there are X everywhere, so you can execute from anywhere. So we can put new code as parameter data in that parameter section. That does come with some caveats, though. And first of all, we have this wiping risk again, right? If one of these unopportune resets occurs and wipes the page, well, now we've wiped all the parameters in that page, right? And there's actually quite important configuration data in there. We got a little bit lucky that the telemetry section was the one that was wiped, because if the comms section was erased, it wouldn't be so cool. Fortunately, there is one single unused parameter section that we can use for this. And so this gets us 8 kilobytes of space where we can put new code in. Actually, we only get 4 kilobytes of space because they have a bug in their code, which means that the top bit is masked off, so only the lower half is accessible. Well, actually, we only get 2 kilobytes of space because another unrelated bug. That means, yeah. So this does not fit a full 300 kilobyte software image, it turns out. So we're going to have to somehow leave the existing onboard software running and sort of enhance it. So how are we going to do that? Well, the first thing we're going to need is for someone to even gain code execution and gain execution of our code. That turns out to be the easy part, because there's this telecommand, command jump to image, which is intended to switch between those 3 different software images in the early part of Flash. But you can totally use that to go to anywhere else. And this is intended to be like a permanent transfer of control. But actually, this is implemented using a C function pointer call. And so you can totally actually just return from this and leave the original onboard software running. It reacts a little bit weird, but it turns out to be fine. And so we can do that. So this gets us code execution and leaves the original software running. But now the question is, how can we persist ourselves to keep running after that? Because we can't just, we have to change the onboard software somehow, right? But we can't change the flash. One, because we're running out of it, right? So that would be a bank conflict. We can't both read from it and write to it. But even if we somehow jumped through SRAM or something, it would be very risky, because again, we have to do this erase, rewrite thing. And if we erase a page of the onboard software and then try to rewrite into it, and we have a reset, we might just end up bricking the onboard software, which would be not so cool. So the question now becomes, how can we modify the onboard software without modifying Flash? And so we can use a trick for this, and we can use something called C++ virtual function tables. mouthful. But basically, C++, that's the language the onboard software is written in, and that supports inheritance. And so what you can do is you can have a base class, and you can have a derived class, and you can override methods. But the compiler, when you call a function on an object of the base class type, the compiler doesn't know what type that object has, right? It's polymorphic, that's the whole idea. And so the question is, how can the compiler know which implementation to call if it's polymorphic type? And so what the compiler does is, in every object that has a virtual function or derives from something, you have a hidden field at the very start. It's always at offset 0. Not quite, but it's usually at offset 0. And this basically points to a table in Flash that says, for my object, for my type, these are the right functions to call. Now, the good thing is that's an SRAM, right? Because this is because it's part of the object variables. And C++ inheritance is actually used quite heavily in the onboard software. And specifically what they do is, for each part of the onboard software, they have these command interface structures. They have like a command interface for power commands and a command interface for attitude control command, whatever. But these are global variables, and so they are located at fixed addresses in SRAM, and we can find those addresses by disassembling the firmware images. So what we can do is we can hijack that vtable pointer ourselves to point at our own implementation and hijack control flow at that point specifically, when we can reuse all of the code for command passing from the existing onboard software without having to do it ourselves. So let's have a look at how that looks like. So this is some example code. It's paraphrased, but the onboard computer, this is what the onboard computer does when it gets a command. So it's going to be like, okay, is this the loader subsystem, or is this the PCU subsystem? And based on that, it's going to call the execute function of some global object. Now, let's say it's a loader command. So it's going to then, because the loader command handler is one of these polymorphic types, right? It's going to look up in memory, in SRAM, that virtual function table pointer. That pointer will then point to a virtual function table in Flash again, and that then has the actual pointer to the implementation for that type. And so then the compiler can go, okay, I will fetch the pointer and then call that. Okay. So now what we can do is we can intercept the execution here. So we can overwrite this vtable pointer in SRAM to point instead at the parameter Flash, where we put our new little shiny payload that we designed. And so we can give our own replacement vtable that's compatible with the existing vtable and point it at our own handler function. And so what we can do here is we can check if the command code is one of a new telecommand that we would want to add. And if it is, we can handle it. And if it's not, this is the other cool part, we can just directly forward to the loader command handler code and bypass the vtable entirely. And so actually for all the existing commands, we can use the existing onboard software. So we only have to implement, we don't have to re-implement any code from the existing onboard software, we can implement just our new code. And this helps really a lot in keeping with this 2 kilobyte size boundary. So that all works and it's great. The problem you run into is one of bandwidth. So a software image, let's do some math. A software image is 300 kilobytes big. And unfortunately, you're limited to 4 bytes of payload per telecommand. That's a limitation in the COM system we can't change. And there's also another limitation in the COM system that says we can only do 1 command per second, because it's intended you do 1 command per one of these gaps. We get 15 minutes per each pass of the satellite, and we get 6 passes a day. Very optimistically, we made up at least 2 weeks for a software update, which is quite a lot. And realistically, it's going to be like 5 times as long, probably, because it doesn't go that way. And we might want to do more than 1 software update, too. So the question is, can we do any better? And the answer is we can. Because, in fact, the designers of BEESAT originally wanted to do software updates, so they added support for longer telecommands. So they started that, but then abandoned it. And so the COM system supports it. Perfect. The OBC supports it, too. Unfortunately, they don't support the same version of the protocol, and so there's an incompatibility, and they don't accept each other. So we have to fix that. So this is the problem. We're going to start at the bottom this time. Every one of these rectangles is a message sent on the CAN bus with 8 bytes of payload. And so the way these transactions on the CAN bus work is, you want to send more than 8 bytes, you have multiple messages. You have a start message in the bottom left there with that control number that contains a pseudo-random control number. Then you have a bunch of data messages, and then you have a stop message. And the stop message contains that control number again, and that's compared to make sure that you didn't have 2 transactions clashing on top of each other. And you also have a checksum over all the data that was sent in that transaction. The problem is the COM system added an additional data message. And so what will happen is when the OBC receives the message from the COM system, it will reinterpret that last n+1 data message from the COM as the stop message. And we'll try to use it as the control number and checksum. And so, of course, that's not going to work, right? Yeah, so that's not going to work because it's going to misinterpret the numbers. So what do we do about that? what we can do is we can actually hijack the interrupt handler of the onboard software. So what we're going to do is there's an interrupt handler, which gets called when a CAN message is received, and we can overwrite that with our own custom code. And that's not a lot of code to reproduce, so we can simply copy the existing code and add our own. And what we can do is we can listen for this n+1 of data message, and if it arrives, we're going to simply store it to the right place in SRAM and then discard it. And that way, the onboard software never receives that spurious message and misinterprets it as a stop message. Then we're going to wait for that stop message, and we're going to use that data we saved away to modify the checksum so that it looks like it's correct, because that checksum, of course, is including that n+1 of data message, so we have to remove that out of there to make it work. And then we forward it onto the main onboard software. OK, perfect. We have a plan. Test it on the laboratory model. It works great. Time to do it in space. So we came up with a little plan. We have to somehow get this 2 kilobyte image into space. And the risk we again deal with is this reset risk, that if there's an accidental reset, we might burn that one unused parameter page we have, and then we're out of unused pages. And so we came up with a sort of 3-step plan to do this. We first have a little safety image, and that's just 4 instructions. And we put that not in the unused section, but in the least important section. So if that breaks during those 4 bytes of upload, the spacecraft is still going to be fine. It's going to lose some functionality, but it's going to be fine. And so all that safety image does is it's just going to call a flash write to reset the size field of the unused page and unburn it, right? So we can use it to write to again. So this gives us assurance that even if we burn a page, we can recover from that. The next thing we have is we have a loader image, and this is just some convenience features, because it actually takes quite a while to upload the 2 kilobytes in just 4-byte chunks. And so we include some convenience features, like we fixed the telemetry system temporarily, so we get some telemetry back. And we also did some, like the 60-second timeout, we brought that back, so we don't have to worry about it just sending for 70 minutes or something. And then finally, we're going to upload the main software image. And that contains all the actual features we talked about just now. So this ends up being about 600 commands, which takes a while. But OK, let's get started. So we started with the safety image, uploaded that. That all went great. We didn't have to use it yet, so that's great. We then installed that loader image, and that also worked, right? And we got some telemetry back, and the temporary fixes seemed to work. Perfect. Now, while uploading that main image, I noticed something interesting. So this is the main switch page, which contains all the different switches on the spacecraft and tells you what's on and what's off. And I would like to draw your attention to the camera slide there. So I was doing this, and then at some point, I sent a flash dump command, that unused command we talked about, to see how many of the commands I had sent up actually got received, and which ones weren't received properly, so I know where there's gaps. And it turns out, after I did that, the camera turned on, which is kind of interesting, because I did not command the camera to turn on. So I was a little bit worried at this point, I might be honest. But I eventually found the bug. So this is the excerpt of the code. Does anyone see the bug? So they forgot a break statement. So whenever you do a flash dump command, you also command the satellite to take a picture. We did that quite a lot, actually. Oopsie. Now, the good thing is, I talked with the project lead, and he told me the camera is actually incomplete, the software. It has never worked. They've never taken any image using this camera, and which is kind of sad, right? And so all it's going to do is it's going to power off by default after 60 seconds, and in that time consume 60 milliamps, which is like fine, right? We can deal with it. And the other thing is, there was really no alternative. Like, we need that command to dump the flash down. So we're just going to continue onwards and upwards. So, ready? We upload everything. It took 9 passes to upload that entire image. And then we send the magical tele command to rewrite that parameter section to give the proper value back. And for the first time in, well, still 10 years, we actually got the full set of telemetry down, including all the voltages and everything. And so now we've restored the spacecraft back to the factory state it was in before it happened in 2013. So now it's time for my favorite chapter. Now I could bore you with a bunch of, so first of all, what you have to do now, right? You have to recommission the spacecraft. So you have to go for every single system and check everything out, right? And I could do that, and it's kind of boring. The spoiler is everything is working fine. But what I really want to focus on, because this is actually what found my interest in the satellite, is the camera. because a satellite that doesn't take pictures, so the camera software is incomplete, we learned, but no one could actually tell me what exactly is missing from this camera software. The problem is, unfortunately, I bricked the laboratory model camera, because what happened is then, if you remember, we tried to assemble a new development setup, right, from Frankenstein parts. I used the right PCB, but a strapping resistor on that PCB was in the wrong place. And so what I did is, instead of connecting the camera to the onboard computer, I connected the camera to a power switch. The camera was not very happy about that, I think. I have not tried swapping it back yet. So it's now drawing 25, it very briefly drew 80 milliamps, and now it's drawing 25 milliamps. I think that's a bad sign. It's also not sold anymore, except for like Turkish equivalent of eBay Kleinanzeigen, which I cannot get to. If you happen to have one you don't need, hit me up. Fortunately, we found out earlier that the flight model camera, that's drawing 60 milliamps, as it should, right? So that seems functional. So we're going to do some on-orbit debugging. So we can use the flash dump command to actually download from SRAM instead. Because it's just a mem copy, it turns out. Now, which again, that would try and take a picture in itself, but we can try and take a picture while we're taking a picture, and it sort of works out. So we can do that, and so I did that. And this is one of the transactions from the camera to the OBCI trace. And if you look at the datasheet for the camera, this says, I have taken an image of size 9.5 kilobytes, and I'm ready to downlink to you. Interesting. I thought this thing was not supposed to work. What happens if I press the download button? It does work. Now, I can't tell you if at some point in the last 10 years it started working, or if it's always been working. I don't really know. But so this is to explain the picture. In the top left, that's actually Earth. But the auto exposure has moved really far down, because it turns out getting the proper exposure of auto exposure on something that's 50% black and 50% pure bright is very difficult. And so that in the bottom right, that's actually the sun blinding the thing. But with a little bit of practice, we can actually get the attitude control working too, and actually point it at the Earth and take some cool pictures. So it's not the greatest quality of camera, let's be honest. It's 640 by 480. You will also notice there's a small little, the bottom right isn't quite right. That's because someone wrote less than instead of less equals. So we get some nice pictures. So this is Poland, so that little star structure, I'm not sure if you can see it, but there's sort of star thing there. If you look at Google Maps, that's actually Warsaw. And then we can see other pictures. So this is Hungary. And in the top right, you can see that like a little more jagged than a cloud would be, and that's actually the Alps from above. And then down there is somewhere is Budapest. Now this is where we come to my biggest problem with this talk. I tried so hard to get a picture of Hamburg, but for the last month, it has been non-stop cloudy over Europe. And so the best I can do is this. So north is actually to the left in this image. In the bottom left is Hamburg, I promise. And we can get finally a nice little image of the sun rising. And I'm actually very happy to present the first research result from BEESAT in the past 10 years. The Earth is in fact round. And so this is where we are today. Everything that's green is we tested and it's working. Everything that's blue is we haven't tested it. So the only thing that's slightly not working is, it's still working. There's one sensor which is drawing like 20 milliamps more than it should, but it's still working. So this thing is basically factory new, which is great. And so I'm actually a little bit ahead of time, but I might do a bonus slide. But I want to close on a little note about reliability. So this is a plot from a paper, and this plots CubeSat reliability over time. So the x-axis is 2 years here, that's time, and then the y-axis is reliability. Now the first thing you notice is this plot does not start off at 1. It starts off at 0.8. So 20% of these things they're called dead on arrival, like they never work to begin with. And then after 2 years, you drop to 60% reliability. And so we've been going for 15 years now, and this thing is working like brand new, basically. And so we've made some fun of the developers, a little bit of some of the code, right, because it's funny. But I really want to thank the entire BEESAT-1 team for making this awesome spacecraft that still works after 15 years. And I would like to thank some people from university, my thesis advisor who allowed me to do this as my bachelor's thesis, which was cool, and some other people. And with that, I'm actually done, and I would like to ask if you have any questions.
Amazing.
Thank you very much.
That was amazing. No one can tell me that software engineering isn't creative. That was really cool. So, gentlemen, creatures, ladies, people of the Earth, if you have questions, and space, if you have questions, please line up. There are microphones. And also we have Signal Angels who is reading your questions from the internet.
And while you're getting ready, I also have a question, which you've probably also already been asked. You have successfully captured a vehicle in space. Would you consider yourself a space pirate?
You make a very good point. I technically had permission, which I think means it's not technically piracy, but technically also the person I asked didn't own the spacecraft.
True, true.
So perhaps by proxy. I'm going to remember that. I'll figure it out.
Yeah, thank you very much. And then I see we also already have people at the microphones. I would start with microphone number 1 here. Question, please.
Yes, thank you. Great talk. You showed at us that you have basically fixed computer number 2. Have you considered computer number 1 as well?
An excellent question. I have a slide for that. So we fixed computer number 1 because that's the one that was active after the failure in 2013. Eventually, I actually found the logs from 2011 because they were migrated to a different system, so I didn't have them. It turns out it's actually quite interesting. All of the symptoms are reversed. Instead of sending indefinitely, the satellite sends 1 frame and then stops immediately. And instead of not containing data, the frames do contain data, but garbage. And so I have a theory on this, and I eventually figured out in the datasheet of the flash chip, what happens is there's something called pre-programming, which is you don't want to erase the same 1 bits back to 1 over and over again, as far as I understand it. So what you do is you program everything to zeros before you program it to 1. And so what I think happened is this reset, in this case on OBC number 0, it interrupted that pre-programming step, and so instead of all the parameters being really high, they're all 0. And so that completely reverses the symptoms. So it's a theory. We're probably not going to switch the onboard computer because there's a risk that in the last 10 years it broke. So I would really like to, but there's nothing to be gained for it, so it's difficult to justify it. But at some point, OBC number 1 might fail, and if that happens, we will have to. But it looks like, I think it's the same malfunction, even though it looks differently.
Thank you.
The interwebs has a question.
Yeah, there are multiple questions. Let's start with, how do you go about figuring this out? Is there only the source code, or do you have other documentation to look into it?
So it's sparse, right? Because nowadays they do this better, but back then this was like relatively early days, and there wasn't a lot of archival of stuff. So we actually had to do this thing of emailing people to get the software images. It was actually kind of difficult because for some software images you don't know if it's the right one unless you get the guarantee. The thing is, the reason I actually came to this is because I was working on BEESAT-9, I had the source code for that thing. And I figured out Sunday evening at 1 a.m. that if you go far enough back in the Git history, you get to BEESAT-1. And so I was bored one Sunday night and was like, okay, let's see if we can figure it out. And it turns out, yes, we can. But the documentation is kind of sparse. It's a lot of the actual work I did was like, this whole thing took a while, right? But a lot of that was just like running around and getting the right documentation from people. But I have a pretty complete set now, fortunately. But some components I still don't have it for. But fortunately for the components I did need for this, I had it. I had a lot of help from the people at my university because they do still operate satellites. So for example, we had to like fix the ground station because the ground station was not meant to operate with this old satellite anymore. They had upgraded since, so we had to actually backport all of that stuff to get the ground station working and stuff like that. So there was a lot of human labor of like going around and talking to people involved. But everyone was super helpful and gave their time for us because they all want. This is, I think, the oldest satellite that TU Berlin still controls themselves, I think. And so it's kind of like a mascot, I suppose. So everyone wanted to help, which is really cool.
Thank you.
Yes, and then there is another question on microphone number 3, please.
Thank you very much for the talk. Since you started now bug fixing, do you will you continue with the camera system now too?
Yeah, so the question is what do you do with it now, right? So there was some consideration if you take the code from the modern BEESAT satellites and like backport everything. The problem is like some hardware was changed, so it's like kind of difficult. So I think I do want to do some more software updates for this to get like, it's like a test bed at this point, right? Like I want to get, one thing I really would like to do, right? I want to fix the camera bug, right? I want to change the exposure on that. I would really like to get video if I can, because that would be cool. But it might be a little bit difficult. So, but like the primary mission at this point is just keep this thing alive as long as possible, because it's going to decay in 2047 is the projection. If it's still going in 2047, I will be happy. But yeah.
Amazing, thank you. The internet has another question.
Yes, how often does the satellite reboot, and is this normal behavior?
Yeah, it's an interesting question, right? Because having that reset, so it resets quite frequently actually, but that's because there's a bug on it that means in safe mode it resets every 15 minutes or so. But actually it would still be a pretty big coincidence actually to have it reset at exactly the right point in time, but in that step between the flash erase and rewrite, wouldn't it? So there's actually, this is some of the code that does that. So they erase the page, right? And that actually takes a little while. And so they have this timeout function that waits until the erase is done. Now sometimes on the flash chip, the erase fails. And so they have a timeout there to retry it in that case. But if you look at this code for a second, you will see that this is kind of backwards. What they meant to write was, while we're not done, and the time that's elapsed is less than 300 milliseconds, we're going to keep waiting. What they actually wrote is, while we're not done, or we've been waiting for 300 milliseconds or longer, we're going to keep waiting indefinitely. And so what happens is this gets into an infinite loop in case of a single timeout, and then there's a watchdog timer which doesn't get triggered, and that actually hard resets the satellite by itself. So there's actually bugs which can lead to a reset precisely in this moment, and that's what makes this more likely.
Thank you. We have time for another question, and up there is another one at the microphone.
Thank you very much for this amazing talk. My question, why wasn't the parameter page or the whole parameter section of the flash stored multiple times like the firmware? Because it's like common practice for such things, like even on the NES save states.
So when I first talked about it with the project lead, they had a design that said these parameter pages are guarded by checksums. And so what they would do is, in case of a checksum failure, they would simply reload reasonable defaults. And that would sort of protect, in a similar way to storing in multiple times, that would protect against that. The problem is, this is the only line that mentions these checksums. They're never actually checked or written anywhere, so they're not. So this is the kind of thing where they probably planned for this, but then ran out of time to do it, because they had a pretty hectic launch schedule, as I understand it. So they tried to do this, but then ran out of time to do this.
Thank you very much.
I think the internet has an additional question.
Yeah, there is a question, how do you get involved in a project like this when you're not studying at TUBE? Do you have an idea about that? And another question, or they're adding, if you're an allowed pirate, you're a space privateer.
Ooh, I dig space privateer, that's good. Okay, how do you get involved with this? Yeah, it's kind of tricky, right? TU Berlin has this thing, right? It's a class they did. I imagine other universities have the same problem with having old spacecraft they can operate, because I think they're funded similarly. I think, I don't want to say the wrong one, but there's another university which has, I think, Flying Laptop, which is another, Stuttgart, thank you. I was looking at you. So they have a similar student thing like that. So maybe check if your university has some old satellites they don't need. They might, you know. Beyond that, yeah. I am privileged, right, I guess, that my university had this. So I got lucky because I got to take this class. But check out your local university, because they might have something else. Or if they don't have, maybe you can ask them if all their old satellites are not funded anymore. And maybe you can start something. That would be cool, too.
Thank you. Additional questions from the internet? I see at least microphone number 4 lining up.
Is there a possibility to get the signal from the satellite for ourselves?
Yeah. So BEESAT is on the amateur radio band. It's 445.95 megahertz. And if you're in Europe, you can totally just receive on that band and decode it yourself. And because it's amateur radio, actually all the documentation, how the telemetry is encoded and stuff, is actually public. It has to be public because it's amateur radio. And so you can totally just receive it yourself. It's not always transmitting over Europe, right? It's only transmitting when we're commanding it. But if there's a morning pass and you try it a few times, you can get lucky on it and receive it. Or just text me and I'll activate it for you. There's also because it's an amateur radio satellite, also an amateur radio service on there. It has a digipeater, which is there's actually a format in which you can send messages up to it yourself, and it will relay them back down. And the cool thing about that is, if you're in Berlin and link it up, and it links back down, you can see it everywhere the satellite has a footprint, right? And so it's like a relay mechanism. So actually that you can send to.
Thank you very much. There is another question up again.
Hi, hello. Thanks for your awesome work. Looks like a cool project. Do you happen to know what kind of real-time OS is running on BEESAT-1? I think one or two of my old professors might be involved in that project before they move to Würzburg. Are you in contact with Professor Montenegro, maybe?
So, I think I know what real-time operating system. You're talking about Rodos, right?
Yes.
It is indeed running on Rodos, yeah.
Okay.
Unfortunately, no, I shouldn't say that. I'm told it got much better after this. Oh no, actually, I'm wrong. Sorry. So
Isn't it running on BOSS or something?
Everything after BEESAT-2 runs on Rodos. BEESAT-1 runs on something else. BEESAT-1 runs on something called TinyBOSS, and that's a custom thing. But I think that's also from Würzburg, to be honest. I'm not sure. But I'm actually not in contact with them because all of this was like before my time, right? I'm just doing archaeology on these things instead of developing them.
If you want me to, I can establish some form of contact with Professor Monti.
I don't know them, but text me on Fedi after and we can talk maybe.
Yeah, no problem. Thanks for your work.
Yeah, of course.
Thank you. I imagine these complicated emails asking for, could you tell me something about this ancient technology?
It's quite helpful, actually.
It sounds like. Microphone number 1 has a question.
Yes, about the data retention of the flash chip. Was there a number provided by the manufacturer?
So I did the math on this. The thing is that I think the retention of the retention is how much long it keeps how many cycles and how long it keeps it, right? So I did the math on this on if we actually need to worry about that within the lifetime of the satellite. It's rated for, I think, 1 million cycles and 10-year retention. But the way I understand it, I'm not an expert on this, but the way I understand it, the retention is spec for the maximum temperature, and that's 70 degrees. And typically in space, we're cycling between 20 and minus 10 degrees. And so I found a formula that says we should have like 1,000 years of flash retention time. So I think we'll be fine on that, fortunately.
Thank you. At microphone number 3 is our next question.
Yeah, thank you for the awesome talk. It was really good. My question is there some security built into the telemetry commands to prevent people from fucking up the satellite now that you've fixed it?
Telemetry, everything that goes down is unencrypted. It has to be unencrypted. There's an exemption in the amateur radio standard for encrypting of uplink telemetry. I can't, unfortunately, talk about exactly what they do for BEESAT-1. I can say in general, so CCSDS standardizes both telemetry and telecommands, and there's actually a standard for encrypting both directions. It's called Space Data Link Security, and this is basically like transport layer security. So this supports AES, GCM, counter mode, and HMAC, I think. But I can't tell you exactly what they do on BEESAT-1, unfortunately.
Thank you.
Additional questions from the internet?
Yeah, would it help to fly along the path of the satellite to have some more time to upload your code?
I mean, let's see. How fast is an airplane moving compared to 7.5 kilometers per second? So one thing which does help is like putting your ground station in a different place, right? So TU Berlin also has one at both the North Pole and, no, not quite the North Pole, but like in Svalbard and near the South Pole. And because of this north-south rotation, actually, if the further north your ground station is, the more time you have to uplink and downlink. But because we also had to make some ground station changes to make it compatible again, we actually didn't use that ground station for this. Ultimately, like, yeah, more bandwidth, more better. For what we did now, we didn't do a full software update yet, right? So we just did this fix, and that was possible in like 10 passes or so. So for that, it was fine. For a long time, if you have a better ground station side, that helps, right? Yeah.
You said something about BEESAT. Well, if there's a BEESAT-1, there should be a BEESAT-2. What about using these as proxies?
So the interesting thing is there's BEESAT-1 and there's 2 to 13. So this is actually the ground for a very long set of satellites. But the sad thing is, so BEESAT-1 is in a 700-kilometer orbit, right? And the orbit height directly correlates with how long it stays in space. And so actually there's only one other BEESAT left. All of the other ones re-entered the atmosphere and burned up last year. So BEESAT-1 will actually, BEESAT-1, the first BEESAT, will become the last BEESAT-2. So unfortunately, we can't use them for testing anymore. But it was helpful because you can compare some things because the hardware is similar in some cases. So for example, because we don't have a laboratory model for the sun sensors anymore, for some of the components anymore, we can check BEESAT, one of the different BEESATs, the historical data, and can check if the data is in line with what we would expect and stuff. And of course, I also got that class trained me to operate BEESAT-9, which is similar still in construction to BEESAT-1, so I had a head start in learning how to operate. So it's helped a little bit, but unfortunately, they're gone now. We're very sad about that.
Thank you. I can imagine that this doesn't happen too often, that a satellite is getting lost in space. But in case it does, do you have anything in mind? Is there a satellite where you wish that you could play around with a bit?
Ooh. The thing is, people don't usually tell you about their failing spacecraft. There's another one from TU Berlin I want to look at, called Technische, which is not failing, but there's another thing ongoing down there. If you have one that's broken and you think might be fixable, do please contact me. I would love to. Unfortunately, they're pretty hard to come by, unfortunately, it turns out, yeah.
Oh, you don't say.
Yeah, it's I don't know. That's still a 5-digit number, but they're doing more now, so maybe we'll get more. I don't know.
Very interesting, thank you.
The internet has additional questions. We have still a little time for the questions from the internet.
There is a question: why would you send up a satellite in orbit with a not working payload?
It's a good question. So I mentioned that BEESAT-1 is the 33rd CubeSat in space, and so the actual payload is not the camera. This was a technology demonstration mission to demonstrate miniaturized components, right? That you can actually get all these things in such a small form factor. And so this is actually the second CubeSat at all that flew with 3 reaction wheels. And so actually the actual payload is the reaction wheels. And this is like a system to point the satellite in the right direction. And so the camera is more of a dummy payload, which is just there to demonstrate that you can have a payload on it. But the actual payload is the reaction wheels. And those actually did work fine. And they spent a lot of time making sure that they do work. That's a good question.
Thank you. We're nearly by the end of our time slot. I would like to ask you if you would have time afterwards for a quick Q&A, or if you would be available for other people to contact you with questions.
Absolutely.
Then, if you have additional questions, please proceed and please welcome and thank for the interesting talk and the creativity behind that. Piston Miner, thank you very much.
Thank you.
Big applause.